Hello, good day everyone. I am Riyan Mahalail from BSed Mathematics 3A. So, let me discuss to you what is matrix diagonalization. So, what is matrix diagonalization? Matrix diagonalization is the process of transforming a square matrix into a diagonal one. So, we do this using similarity transformation, and which takes the formula A equals to PDP inverse, which is D is represent as a diagonal matrix and P is an invertible matrix composed of eigenvectors of A. So, why diagonalize? So, diagonalizing a matrix has a major of computational advantage. It makes it very easy to raise a matrix to a power. If we can write A as a PDP raised to negative 1, then A raised to n equals to PD raised to n P raised to negative 1. This is extremely helpful in solving system in differential equations and simplifying linear transformation. So let's proceed to the diagonalizable matrices. A matrix is diagonalizable if it has no defective eigenvalues, and it also defective in the eigenvalue, an eigenvalue whose geometric multiplicity is less than its algebraic multiplicity. However, not every matrix is diagonalizable. A matrix is only diagonalizable if it does not have any defective eigenvalues. A defective eigenvalue is one where the number of linearly independent eigenvectors, also called geometric multiplicity, is less than its algebraic multiplicity, which is the number of times the eigenvalue appears as a root. Next is condition for diagonalization. So what ensures a matrix can be diagonalized? The key condition is that the matrix must have n linearly independent eigenvectors for an n by n matrix. In other words, the geometric multiplicity of each eigenvalue must equal its algebraic multiplicity. Next is the similarity transformations. Two square matrices A and B are similar. If B equals to P raised to negative 1, AP where P is invertible. Similar matrices are essentially the same matrix represented in different bases. As a result, they share many important properties such as rank, trace, determinant, and eigenvalues with the same multiplicities. So to conclude, matrix diagonalization is a useful tool for simplifying matrix operations, especially when working with matrix powers. However, not all matrices are diagonalizable. Lastly, similarity transformations play a central role in diagonalization and help preserve important matrix properties. That's all for my report. Thank you.
So let's now proceed to diagonalizable matrix. So we can now provide a definition of diagonalizable matrix. So let A be a K by K matrix. We say that A is diagonalizable if and only if it is similar to a diagonal matrix. So in other words, when A is diagonalizable, then there exists an invertible matrix P such that D is equals to the inverse of P times AP, where D is a diagonal matrix that is a matrix whose non-diagonal entries are 0. So for example, define the 2 by 2 matrix where A is negative 1, 0, 2, and 3. And then the P is 1 half, 1, negative 1 half, and 0. So the inverse of P is 0, negative 2, 1, and 1. So the similarity transformation looks like this. The inverse of P, A times P. So let's say that inverse of P is 0, negative 2, 1, and 1. And A is negative 1, 0, 2, and 3. And then P is 1 half, 1, negative 1 half, and 0. So it is equals to, let's say, the inverse of P steady, 0, negative 2, 1, and 1. And then we are going to multiply A and P. So negative 1 times 1 half plus 2 times 1, and then 0 times 1 half plus 3 times 1. So the other one is negative 1 times negative 1 half, and then plus 2 times 0, and then 0 times negative 1 half, and plus 3 times 0. So it is equivalent to study the inverse. So 0, negative 2, 1, and 1. And then the multiplied A and P, 3 half, and 3, then 1 half, and 0. So we are now going to multiply the inverse of P and the equivalent of A and P. So 0 times 3 half plus 1 times 3. So remember the row and column multiplication. So and then negative 2 times 3 half plus 1 times 3. And then the other side is 0 times 1 half plus 1 times 0. And then below is negative 2 times 1 half plus 1 times 0. So that will give us the diagonal matrix of 3, 0, 0, negative 1. So as a result, hence A is diagonalizable.
I am Jerick and Candido. My topic is relation to eigenvalues and eigenvectors are fundamental in linear algebra. We can write the diagonalization D equals P raised to 1 AP as AP equals PD. The K column of AP is equal to AP point K, where P point K is the K column of P. If you are partial, revise the lecture on matrix multiplication and linear combinations. The K column of P is equal to PD point K, where D point K is the K column of D. In turn, PD point K is a linear combination of the columns of P with coefficients taken from the vector D. Since D is diagonal, the only non-zero entry of D point K is D double KP. Therefore, PD point K equals D double KP point K. Thus, we have arrived at the conclusions that AP point K equals D double KP point K. The latter equality means that P point K is an eigenvector of A associated to the eigenvalue D double K. This is true for K equals 1, K, thus the diagonal elements of D are the eigenvalues of A and the columns of P are the corresponding eigenvectors. The matrix P used
in the diagonalization must be invertible. Therefore, its columns must be linearly independent. State differently, there must be k linearly independent eigenvectors of A. In the lecture of the linear independence of eigenvector, we have discussed the fact for some k multiply k matrix called defective matrix, it is not possible to find k linearly independent eigenvectors. A matrix is defective when it has at least one repeated eigenvalue whose geometric multiplicity is strictly less than its algebraic multiplicity, called a defective eigenvalue. Therefore, defective matrix cannot be diagonalized. The next proposition summarizes what we have discussed thus far. Proposition A k multiply K matrix A is diagonalizable if and only if it does not have any defective eigenvalue. Proof: remember that if all the eigenvalues of A are density, then A does not have any defective eigenvalue. Therefore, possessing density eigenvalue is a sufficient condition for diagonalizability.
How to diagonalize a matrix? Suppose we are given a matrix A and we are told to diagonalize it. How are we going to do it? The answer has already been given in the previous proof, but it is worth repeating. We provide the answer as a recipe for diagonalization. First, compute the eigenvalues of A. Second, check that no eigenvalues is defective. If any eigenvalue is defective, then the matrix cannot be diagonalized. Otherwise, you can go to the next step. Third, for each eigenvalue, find as many linearly independent and eigenvectors as you can. Fourth, adjoin all the eigenvectors so as to form a full rank matrix P. 5. Build a diagonal matrix D whose diagonal elements are the eigenvalues of A. 6. The diagonalization is done. D is equal to identity of P times AP. Importantly, we need to follow the same order when we build P and D. If a certain eigenvalue has been put at the intersection of the kth column and the kth row of D, then its corresponding eigenvector must be placed in the kth column of P. Example, define the 2 by 2 matrix. A is equal to 5, negative 3, 6, and negative 4. The eigenvalues lambda solve the characteristic equation determinant open parenthesis lambda I minus A close parenthesis is equal to 0. Let us compute the determinant. That open parenthesis lambda I minus A close parenthesis is equal to that open parenthesis and open bracket lambda 0 0 lambda close bracket minus open bracket 5 negative 3 6 negative 4 close bracket and close parenthesis is equal to that open parenthesis open bracket lambda minus 5 3 negative 6 lambda plus 4 close bracket and close parenthesis is equal to open parenthesis lambda minus 5 close parenthesis open parenthesis lambda plus 4 close parenthesis minus 3 times open parenthesis minus 6 close parenthesis is equal to lambda squared plus 4 lambda minus 5 lambda minus 20 plus 18, which is equal to lambda squared minus lambda minus 2. And that is equal to open parenthesis lambda plus 1 close parenthesis open parenthesis lambda minus 2 close parenthesis. Thus, there are two eigenvalues. Lambda sub 1 is equal to negative 1 and lambda sub 2 is equal to 2. There are no repeated eigenvalues and as a consequence, no defective eigenvalues. Therefore, A is diagonalizable. The eigenvectors x sub 1 associated to lambda sub 1 solve open parenthesis lambda sub 1 I minus A close parenthesis x sub 1 is equal to 0. Since lambda sub 1 I minus A is equal to negative 6 3, negative 6, 3, we can choose. For example, x sub 1 is equal to 1, 2. Moreover, lambda sub 2 I minus a is equal to negative 3, 3, negative 6, and 6. So we can choose as an eigenvectors associated to lambda sub 2 the following vectors. X sub 2 is equal to 1, 1. Therefore, the diagonal matrix of eigenvalues is D, open bracket, lambda sub 1, 0, 0, lambda sub 2, close bracket is equal to, open bracket, negative 1, 0, 0, 2, close bracket. And the invertible matrix of eigenvectors is P equals, open bracket, x sub 1, x sub 2, close bracket is equal to, open bracket, 1, 1, 2, and 1, close bracket.
To continue with the last topic, the diagonalization is not unique. Provided a mix A is diagonalizable, there is no unique way to diagonalize it. For example, we can change the order in which the eigenvalues are put on the diagonal of D, or we can replace a column of P with a scalar multiple of itself. So if there is a repeated eigenvalue, we can choose a different basis for its eigenspace. For example, for instance, in the previous example, we could have defined D equals to the matrix of lambda sub 2, 0, and 0, lambda sub 1. So, or it is an equivalent to 2, 0, 0, negative 1. And P is equals to x sub 2 and x sub 1, wherein it is equivalent to 1, 1, 1, 2. So, another possibility would have been to choose x sub 2 is equals to negative 1 and negative 1. So, and the P is equals to x sub 2, x sub 1 is equals to negative 1, negative 1, and 1, 2. So, the most important application of diagonalization is the computation of the matrix powers. So, let D be a diagonal matrix. So, as shown on the screen, that is the way on how we are going to compute the matrix power. So then its nth power can be easily computed by raising its diagonal elements to the nth power also. So if a matrix A is diagonalizable, then A is equals to P times D times the inverse of P, and A raised to the power of n is equals to P times D times the inverse of P times P times D times the inverse of P, and so on and so forth. So this is the n is the repeated times. So it is also equivalent to P times D raised to the power of n times the inverse of C. Thus, all we have to do is to raise A to the nth power to the first diagonalize A if possible. Second, raise the diagonal matrix D to the nth power, which is very easy to do. And third is pre-multiply the matrix D raised to the power n, thus obtained by P, and post-multiply it by inverse of P. And lastly, once a matrix has been diagonalized, it is straightforward to compute its inverse if it is exists. In fact, we have that the inverse of A equals to the quantity of the inverse of P times D times the inverse of P, wherein it is equals to P times the inverse of D times the inverse of P, where, as you can see in the screen, it is the inverse of D formula. So this is the end of our discussion. In behalf of my groups, thank you for watching.